I'll be talking about space data as a service today. I'm from a company called Kuva Space. We're a new space Earth observation company concentrating on a large constellation and hyperspectral. And I'll be talking about our team, a little bit what we are doing at Kuva Space, what's our mission, what's the problem that we're solving. Then I'll describe a little bit more about our solution, some applications. But then the kind of the third part of my talk will be about this data service, like how a data service, space-based data service should be created so that it actually is usable and high quality and reliable. So those are kind of the three parts. And my name is Jarkko Antila. I'm the CEO of Kuva Space. And we have a team of 20 people. We're based in Finland. We have people also elsewhere, but we are 20 people in total currently. And we have vast background on building satellites from all the way from the first satellite of Finland, building different kind of businesses, also creating space-based analytics business, creating camera technology, of course, marketing and sales. So we have the full stack of experience in-house, and that has also translated also to what we have done so far. So even with our small team, we've actually have made three satellite missions with 100% success. So we have 3 satellites up there. The first infrared hyperspectral camera for CubeSat, and the whole CubeSat, of course, been in orbit for 4 years. So some heritage there. So what we're now doing is that we are building a game-changing hyperspectral satellite constellation and data services to solve global existential problems and challenges, meaning climate change, food security, safety and security. And the challenge is that the customers are lacking this continuous, reliable, and affordable commercial monitoring services to manage climate change, food production, and security threats. So the current monitoring methods are not enough. You have satellites, you have drones, airplanes, you have footwork, but there are still great gaps in kind of creating this kind of a digital twin of the Earth, of what's going on every day. So that is what we are kind of where we step in all of this. We are representing mostly a measurement modality which is not there, which is quite critical for this application that I mentioned, and this is hyperspectral. So optical multispectral is more traditional, and there are many so-called new space companies that are doing that. Radar is going up, and there are several companies already have like extensive services, but hyperspectral is still upcoming. There are many companies that are planning and doing like early work on that, but there's really no extensive services available. And hyperspectral is important because it reveals what material is made of. So if you measure, if you would take a hyperspectral image of me, you could say that my shirt is made of cotton, and the jacket is made of cotton and something, and maybe a change of a small color in my skin might be an early sign of melanoma or something like this. So hyperspectral is really powerful in analyzing what things are, whereas radar is seeing shapes and forms, and optical is seeing what the things look like, and maybe the colors as well. So they are also complementary, but hyperspectral is really missing. And so what we are in practice doing is that we are building the most powerful Earth observation monitoring solution, where we combine hyperspectral imaging, small satellites, and AI. So we have a unique camera technology that is, in our opinion at least, the best in the class from many points of view, like quality, flexibility, and size. And with that, we are able to build a big constellation of about 100 satellites to produce about 2 times a day data from anywhere from the Earth. And it's not about the data, or it's actually not about the satellites, it's about the services. And to create the services, we need AI. So we will produce a lot of data. We need AI to both manage how we collect it and then how to crunch in a way the end results for the customers in an automated way. So we're looking things like yield forecast, crop health, different kinds of change detection, carbon sequestration, biodiversity. So just to give you an idea, like how, in a way, a solution for a certain field could look like. We have, for example, on the left, yield forecasting. So Hyperspectral is really good in identifying what kind of species of crops there are, or different kinds of plants. So you can automatically identify plant types and their growth phase. So you know what's growing where and what is the expected yield. But because the constellation is also wide and you get information very often, and you can react immediately if you have, pests or other plant diseases or wildfires or some natural disaster that is actually affecting the crop, other than just how the soil and fertilizing works. So there are many interested parties in that, like commodity traders, insurance companies, governments, and of course farmers. Then we're looking at carbon offset verification, which is a huge field and very needed for stopping climate change, but it's quite wild currently. So the verification methods for whether carbon actually has been sequestrated with certain bio processes is quite unreliable and suffers from bad reputation as well. So with Hyperspectral, we bring in more precise, like biomass measurements for different types, and we can also unlock some of this untapped potential of blue carbon offset. Like in this picture, we have a little bit of kelp growing at sea, and then also agriculture, peatland. There is certainly defense applications for detecting various things automatically. And then there's emission detection monitoring. So, you cannot see methane emissions by your bare eyes from optical or SAR images, but with Hyperspectral, you can do that. And the last example is biodiversity, which is a good example of what Hyperspectral can do in a wide scale as well, combined with a large constellation. You can analyze how many species there are in a certain area and how that changes over time. I mean, plant species. And that is like an indirect indication for the actual biodiversity changes, and that can be then done globally. So not only local measurements. I mentioned earlier that we have know-how in our team from everywhere from building satellites to creating business. So this, I guess, translates to our full value chain. So what we are doing in a supply chain point of view. So we are a vertically integrated company, and we believe that is the right solution in this field where we are. So we build the satellites and the camera. Then the data comes down through ground station network to a cloud data storage, whether it is third party or our own or partly. Then it gets calibrated and corrected by us, analyzed by us, and then depending on the customer, we provide statistical analysis in time series or further products like warnings or recommendations to all kinds of applications. And we aim the time to delivery from the overpass of a satellite to about 1 to 2 hours. So we want to be very extensive in geographically where we serve the customers, but also we want the information to be near real time, so quite timely, so that it's the most useful. So that is what we're doing, and we are in the beginning of this journey, but we are on our way, and we've already developed quite a bit of this AI platform, and actually like 1/3 of our company is already software and AI personnel. Then I go into from what we are doing directly to, you know, how to build a true, in a way, software as a service type of data service in Earth observation. What kind of key properties do you need to have, and what do you need to consider to have it done? So we've listed 8 major properties that I go through here shortly, and also we'll show that, of course, we try to fulfill them all. So first one is availability, and it means that, you know, currently satellite images are such that you typically pre-order some tasking event that, you know, I want to have a picture from you know, this area within the next 2 weeks, and then you get it, but you're never exactly sure when you get it, if you get it, and certainly it's not like covering, and also it's typically just image and not information that an end user could use. So the data availability should be such that there is continuously updating data that is always up to date and available from wherever you need it. So that is our thought, and definitely is one of the key properties of having a subscription-based business. If you don't have the data seamlessly updating everywhere, you can't have that kind of service. The second one is consistency. So the data needs to be harmonized from day to day, from satellite to satellite. The more you can handle this on a hardware level, the better results. So this means that each and every instrument that you make in your satellite needs to, in a way, show the same result. So hyperspectral, like I'm representing hyperspectral here, so that is more like a measurement tool than an imaging tool. Okay, it has the both properties, but it's really not like taking pictures, but it's really analyzing the spectrum that we get for each pixel to analyze what's the content of, or the material content of that pixel. And the more you can do the measurement exactly the same way always, the better it is for comparison of the data. And in a way, old space hasn't had the need for this. I mean, you have like a single satellite for a single purpose, and that gives you images or data, maybe, you know, twice a month or once a month from a certain place, and you do a certain analysis on that, and then, you know, you might compare something in 5 years, but it has not been meant for this continuous data layer. But without this harmonization, there's no automation. So you get data points that cannot be compared from day to day or from satellite to satellite. So that is actually something that is new to Earth observation. It's quite normal in the measurement instrument industry on Earth, where you make, say, 10,000 instruments that needs to show the same measurement result if you go and measure something. This is rather obvious, but it has not been that obvious in space. Quality of the measurements or the pictures, of course, needs to be high enough. You gather a lot of data, you want to automate things, you want to trust the results, so the quality needs to be high enough. It is not enough that you put in, you know, you have a CubeSat and you put some camera to it and you know, get some pictures. If the pictures are not good enough, or if the data does not have the good enough signal to noise ratio for analytics or for the repeatability, it is completely useless at the end. So even for new space, the quality is actually the key to make this whole thing works. And in our case, like hyperspectral imaging instrumentation itself is really hard to make so that it is consistent and it is gives high quality information. And so, you know, that's one of the reasons, I guess, why hyperspectral constellations are not there yet. Then one property that we believe is quite significant is coverage. So, okay, normal Earth observation orbits are such that you can eventually image any spot on Earth at some point. But what I mean with coverage is that you would have this seamless layer of information coming from different places of the Earth. So traditionally, satellite imagery is, or the customers for satellite imagery have been such that it's for a certain purpose at a certain time at a certain place. So this is the kind of the mindset how Earth observation data works. Now suddenly, if you have a full data set of data from everywhere and the automated analytics to give you information every day from vaster areas, then that opens up whole new possibilities for the customers as well to utilize this information. So it is a mindset shift that we need to do in this business, actually, to kind of understand the possibilities for or added value for extended information. And here, of course, when you are gathering a lot of data, you need AI to manage the data gathering, to implement or develop and implement the algorithms to get the right information out. So it is actually a key part of this entire system to have efficient AI included in this. Then we have frequency. So yeah, think fast and slow. We quite often get a question like, okay, so you get data or you get measurements twice a day or once a day. Do people need that information that often? And we say that yes, there are people who actually need it. And then there are people who don't necessarily even understand yet that they will need it. But once it happens, then they will get it. So we have, we kind of say that fast phenomena and slow phenomena. Fast phenomena is quite understandable. Okay, you have natural disasters, wildfires, gas line bursts, you know, enemy troop movement, relocation, anywhere that things happen quickly, and the faster you respond, the better. But then there are phenomena like, you know, trees are growing pretty slowly, and you know, the land mass doesn't move anywhere, and soil doesn't change that quickly. So why should they, you know, have a fast measurement or high revisit? And for that, there are a few things. First of all, if you take several measurements, or if you take measurements often from slowly changing targets, it improves the measurement quality and it improves the forecasting of what's happening. So say you measure a crop field, or you measure a forest, piece of forest somewhere, and you measure it once and you get a result. If you do that 10 times, you actually get basically 3 times better results, even though nothing is changing on the ground, but the signal to noise ratio and your pixel information is improving. There's also one practical thing where this helps. So it minimizes cloud risks. We, of course, are susceptible to cloud coverage disturbance. And sometimes you might have a cloud time or times where you have the cloudiness is quite high. So if you then have a satellite that passes over once every 16 days or something like this, and there's a cloud there, you'll lose a month. If there's another cloud in 16 days, you lose a month and a half. So if you have a measurement every day, you will hit a day and the time of the day where you actually don't have cloud, and so you can actually get information even from this period, and so much less goes unnoticed. And just from like measurement technology or principle point of view, this when you have a lot of measurement point enables outlier detection. So sometimes things happen, and the measurements there might be something unexpected that affects the result. So if you just have one point, you don't have anything to compare it with. But when you have continuous measurement, several points, and you suddenly get one which is off, then you can also analyze whether this was a real event or whether this was just coming from some unknown artifact. So both of these work, and what I kind of think when I think of this, I kind of compare it to insurance for many applications. Like you have a carbon sequestration program, and you approximately know how much trees grow. But if you would have this information coming to you every day, you could show to your customers that this is the real carbon content. And if there would be a wildfire, for example, destroying some of that forest, you would actually get updated information from that then when it happens. So you would not need to kind of wait for the disaster to happen, but you would have, in a way, an insurance on the information side. All right, timeliness. So customers need fresh data. They need it often, but also fresh. So it is important that the data service delivers near real-time data for better decision-making. Otherwise, it cannot be hooked into business processes or decision-making processes. And imagine then, again, like a company that has now been buying single of images and making analytics for that by themselves. Suddenly they get this information daily, in a way like a stock price graph, how much new data and new optimization that brings to the customer. So that is definitely a strong selling point. All right, so cost. Well, that's an obvious thing. If you want to sign customers to your software service platform, SaaS platform, and have them subscribe to an annual subscription, then we cannot have the pricing that is typically out there. So currently, the business model is pay per use. So you need an image, or you need a hypercube, and you pay from $1,000 to $5,000 for each. And of course, like, you want to minimize the amount of images that you buy with that price. If you would have a need for 1,000 images per year, it would be already 1 to 5 million investment per year just for the images. So the annual subscription needs to be the price needs to be low enough so that it is lucrative for the everyday use. And therefore, the EO Constellation itself, the CapEx needs to be low cost. The data gathering needs to be optimized with AI. And what is good with Hyperspectral, which kind of makes this work, is that the raw data needs to be utilized for multiple applications and customers. So it doesn't really work so that you have single image for a single customer, then you don't use it for anything else. It will never become really profitable this way, your business. But if you have a Hypercube where you can crunch out, let's say, 10 products for 30 customers, then it lowers your unit costs significantly and makes this equation work. All right, finally, approaching to the end is usability. So naturally, the information that you provide from the sky, from space, needs to be useful. And it is very rarely useful if you just provide raw data. If you less useful if you provide low quality, scarce, and low frequency raw data. But the thing is that you need to actually in order for your business to scale and to get many customers, you need to have services that have already the answers in a way crunched out. And hyperspectral data, for example, is very complex, and we know also from our some historical knowledge that there's a limited amount of customers that can actually utilize hyperspectral data in an efficient way. So if you just would dump data to the market and hope for the best, that would not be the right way. It would be a slow way, and also the value add would be much lower than optimizing the whole value chain, that how we've done it. So we believe that by controlling the measurement instruments, you can ensure the quality and the kind of how the satellite dances with the camera, and then you are the best to understand what the data is really consisted of, and you yourself have an unlimited basically amount of data from Earth. So you don't need to buy raw data from others in order to make products, but you tap into an unlimited source of data yourself and utilize that to create the products, and you of course need to deliver those through very compelling UX UI solutions, API and so forth, so that the customer gets answers easily on their phone, on their laptop, to their process directly. So those are the 8 points that you have to have, in our opinion, to have an actual, reliable and usable SaaS platform out of an EO service. And how we see that we of course at least check all those boxes, and maybe the Earth observation business is going to that direction in the future when new space is evolving more and more. So thanks from my side. That was my talk today. So yeah, please, if you have any questions, I think we might still have a couple of minutes.
Hi, Jarkko. Thank you for your presentation. We greatly appreciate the insights. And yes, we do have a few minutes, and we have a couple of questions just for people to let them know that if you're watching this live or after recording, you can also find a link included where you can find details about Jarkko and request a private meeting if you're looking to discuss business with him as well. I would highly advise to use that. Questions coming from Antonio, and he says, "Hi, Jarkko. How many satellites do you intend to have in 2026 for a daily coverage? So how many?"
So we have the pipeline is somewhere around 40 satellites in 26. So it is gradually ramping up. So of course, like, depends on the funding situation and all that, but 100 will not be in the next 2 years. It will take a little bit of time, but the 26 about 40, and then 100 couple of years after that.
Mm-hmm. And the second question is from Arnaud, which he asks, what is the resolution of hyperspectral image? Is it lower than 1 meter?
I kind of like this question, but unfortunately we don't have much time. But no, the geometrical pixel size is about 10 meters that we aim to. However, the information pixel, when you are using hyperspectral, we see much smaller things within the pixel. So if you have a 1 square meter thing within the pixel, the hyperspectral will actually dig it out from within that pixel. So the stuff that we can see is much smaller, but they don't appear geometrically like optical resolution.